Pascalcoin Whitepaper V4 January 2019 Albert Molina Pascal Blockchain at gmail.com Herman Schoenfeld Herman at SPHERE10.com Whitepaper authored by Tyler Schwab. Pascalcoin is a next-generation cryptocurrency that pioneers a new tier of scalability comparable to the Visa network, enabled by the SafeBox technology. To become the world's first blockchain independent of historical operations, Pascalcoin possesses unlimited potential. Pascalcoin paves the path towards infinite scaling by allowing new nodes to join the network without the need to download the infinite history of blocks. Instead, they download the latest checkpoint and a few dozen latest blocks in order to fully synchronize with the provably most worked chain. This paves the path towards what this paper coin's infinite scaling. Introduction. Pascalcoin is an innovative cryptocurrency that extends the blockchain paradigm by introducing a new cryptographic structure known as the SafeBox 1. The SafeBox is the ultimate source of truth in Pascalcoin and maintains a ledger balance of all users' funds rather than the full ledger. Structurally, it is like a spreadsheet where each row denotes a bank account, PASA, and each column denotes a property of that account, i.e. Pascal balance, public key, etc. The address of an account is simply its index within the SafeBox with an appended checksum. Every time a new block is minted, the transactions or operations contained within that block are applied to the SafeBox, resulting in a mutated state. The resultant hash of the mutated SafeBox must then be referenced by the subsequent block in order to qualify as the next block. Unlike traditional UTXO-based cryptocurrencies, the blockchain in Pascalcoin is only used to mutate the SafeBox. Whilst a proof-of-work blockchain is still required to facilitate Byzantine consensus up to a checkpoint, it is not permanently required. As a result, the blockchain in Pascalcoin is capable of being deleted without any security compromise. Since only the ledger balance is required for consensus and not the full ledger, Pascalcoin attains exponentially higher transaction throughput per unit of storage than UTXO-based cryptocurrencies. The design philosophy of Pascalcoin is to take Bitcoin to end, rather than abstract and generalize as Ethereum does, simplify and refocus into a single use case optimized currency with advanced features that include but are not limited to the following: instant, zero-fee transactions, theoretical limit of 72,000 TPS, infinitely scalable smart contracts, comprehensive anonymity, addresses are simple account numbers, e.g. 1084. That can be associated with a name, infinitesimal storage requirement for nodes, ASIC, and GPU-resistant algorithm. The Pascalcoin value proposition: infinite scaling. In the context of this document, infinite scaling is defined as the ability of a blockchain-driven network to achieve infinite running time on finite and constant storage. This definition defines a theoretical limit which measures an upper limit of a throughput per unit of storage (KPI). Blockchain architectures with high throughput per unit of storage result in high numbers of users with fast confirmation times and low fees. Networks with low throughput per unit of storage experience slow confirmation times, high fees, and admit an inherent ceiling of users. How does Pascalcoin achieve infinite scaling? Simply put, the blocks in Pascalcoin will be able to be deleted past the checkpointing height of 100. Since new blocks will be appended to the top of the chain and old blocks deleted from the bottom, only a constant number of blocks will ever be required at any time. Checkpoints occur every 100th block and are simply compressed SafeBox archives. When a new full node joins the network, it only downloads the latest checkpoint and a few dozen blocks. In addition, the SafeBox contains block header information in every account segment substructure. This makes it possible for a node to independently compute and verify the cumulative work required to construct the SafeBox structure. It does this by checking that all block headers link transitively as a chain via the SafeBox, recalculating the accumulated work of the SafeBox using the proof-of-work payloads, verifying that the accumulated work of the SafeBox is the largest known in the network. As a result, Pascalcoin achieves exponentially higher throughput per unit of storage than other cryptocurrencies, since a node only needs to store the network throughput and not the aggregated network throughput. Pascalcoin stores the flow of transactions rather than the history of transactions. If the flow is constant, so is the storage. A caveat here is that the SafeBox does grow negligibly with every block, but always in constant amounts and irrespective of the quantity of transactions. For example, by the year 2072 the SafeBox will always be 6 GB in size. whether one transaction occurred or a googolplex. Why other coins cannot achieve similar storage efficiency. Whilst there are other approaches these cryptocurrencies could use, such as pruning, warp sync, finality checkpoints, UTXO snapshotting, etc., there is a fundamental difference. Their new full nodes can only prove they are on most workchain using the infinite history, whereas in Pascalcoin, new nodes can prove they are on the most workchain without the infinite history. Mimblewimble is the closest proposal to achieve what Pascalcoin already does in terms of storage efficiency in UTXO-based cryptocurrencies. Empirical transactions per second in a typical blockchain implementation like Bitcoin. There are three bottlenecks which determine the processing speed: network throughput, number of how many transactions can fill network per second, verification throughput, number of signature and consensus checks per second, blockchain throughput, number of transactions append to the blockchain per second. The network throughput of Pascalcoin and a traditional blockchain is similar because the net propagation speed is calculated based on the amount of bytes needed to communicate operations between nodes. The verification throughput of Pascalcoin and a traditional blockchain are also similar. However, the blockchain throughput for Pascalcoin is on an entirely different level thanks to Pascalcoin's larger block size and its differing mechanism for double spend protection. Pascalcoin allows for exponentially larger block sizes than current cryptocurrencies since nodes only need to keep 100 blocks or so plus the SafeBox checkpoint. This in turn increases the blockchain throughput. More details on the larger block size are given in the next section about the theoretical limit of transactions per second. The double spend protection mechanism entails searching a given blockchain's database, usually based on UTXO, for whether the previous transaction has been spent or not. With the SafeBox, this process is as quick as simply viewing the signer's account state. Thanks to how the SafeBox in its entirety is stored compactly in memory, this process is almost instantaneous in Pascalcoin. In a traditional blockchain, this process is slower because it needs to search in a database saved on disk. The difference between the time needed to search in a saved database on disk, UTXO, versus searching in memory, SafeBox, is significant, leading to a nearly instant transaction speed in Pascalcoin. Multi-threading is used to execute processes in parallel using logical CPUs. A single low-ended CPU will process at least plus 300 operations per second. If 4 CPUs are available, the speed would be at least 300 equals 1,200 operations per second and would be much higher on modern CPUs. Most tests with a 4-core CPU indicate the maximum speed reaching about 1,600 transactions per second. This reflects live performance on the mainnet, given that the proportion of slow nodes is relatively small compared to fast nodes. 1,600 transactions per second as an empirical approximation is among the highest figures attained in any actual blockchain tests on a mainnet to date, if not the highest of all. Theoretical transactions per second. The theoretical limit for transactions per second is much higher than 1,600 transactions per second and is primarily based on Pascalcoin's block size. For about the same amount of storage that a Bitcoin node consumes today, a Pascalcoin could theoretically sustain a block size of 5.62 GB, compared to Bitcoin's 1 MB block size, with a maximum blockchain throughput of 72,000 transactions per second. The maximum blockchain throughput is calculated as follows: maximum blockchain throughput equals maximum blockchain size divide average operation multiplication 1/300. The maximum block size of 5.62 GB is assumed, and the average operation size is 262 bytes. The expression is then divided by 300, the number of seconds in a 5-minute block. This yields the 72,000 transactions per second as a theoretical limit. The theoretical upper limit for Pascalcoin's total throughput is the minimum of the network throughput, verification throughput, and blockchain throughput. This minimum amounts to 72,000 transactions per second, assuming the network and verification throughputs are infinite. The theoretical rationale for assuming network and verification throughputs as infinite is how the blockchain throughput always has a hard, albeit changeable, limit, whereas other throughputs will improve constantly over time. It should be emphasized that Pascalcoin's blockchain throughput is technically unbounded. The maximum number of operations per block is not fixed and could be increased to accommodate any level of mass adoption without any undue burden on nodes, because they only need the last 100 blocks and the latest SafeBox checkpoint. Such an increase in the maximum number of operations per block would lead to a higher block size and consequently a higher blockchain throughput. The maximum block size of 5.62 GB from above was arbitrarily chosen as a reasonable example of Pascalcoin's storage capacity, but if the empirical transactions per second, 1,600, remains fixed, then the maximum block size would be about 0.13 GB. Concretely, storage space for the last 100 blocks is a soft constraint on Pascalcoin's otherwise infinite blockchain throughput. Pascalcoin's blockchain throughput from its efficient memory usage works in tandem with the nearly instant transaction speed of the SafeBox model to enable infinite scalability. It is estimated that Pascalcoin will achieve 100,000 transactions per second as a theoretical limit, assuming a block size of 5.6 GB, with extensive core factoring, optimizations, and hardware configurations. Pascalcoin's total throughput is essentially only limited by Moore's law, storage space, and a highly decentralized architecture. All the specifications above are for Layer -1. With a Layer 2 implementation, Pascalcoin's scalability will be enhanced even further. More information on Pascalcoin's Layer 2 specifications will be released shortly. Cryptographic integrity and security. The SafeBox preserves the cryptographic integrity of the full blockchain, even though nodes are not required to store the full blockchain. That follows from the fact that the SafeBox contains all the block headers used to construct that SafeBox within the SafeBox itself. Each block header makes a hash commitment to the previous SafeBox state, i.e. the state of all accounts at that point in time, and also the previous block header. In this manner, the state and its evolution are preserved by using the difficulties in the block headers. The total work used to evolve that state can then be calculated. Nodes will only adopt the SafeBox with the most work. A distinction should be made between cryptographic integrity, the proof that the SafeBox is hashed correctly from block 0, and cryptographic security, the number of blocks that need to be remined in an attack. The SafeBox retains the full cryptographic integrity and retains 99% of the cryptographic security of a full blockchain. The latter is due to the state attack vector as explained in the following. With regards to the state attack, a distinction should be made between a double spend and a state attack. A double spend refers to an attack involving majority hash power and rolling back already accepted transactions, but not hacking account balances as stored in the SafeBox. A state attack refers to corrupting a balance and trying to cover it up by remining blocks in a way that other nodes cannot detect the hacked balance. With a double spend, Pascalcoin security parallels to that of a secure proof-of-work UXO blockchain and is a function of hash power. The state attack, however, is unique to Pascalcoin and requires an attacker to remine the network median history to succeed. But compared to the standard double spend attack with hash power majority, the state attack is extremely difficult and unrealistic to execute. If a state attacker naively alters an account balance, then it becomes corrupt since the tip block has an invalid SafeBox hash. If the attacker tries to remine the tip block faster than the rest of the honest network such that it links to its corrupted SafeBox, then the honest network can detect the tip block is invalid since they have the last 100 blocks. If a more sophisticated state attacker attempted to remine the last n blocks and do so in a manner that it linked to his corrupted SafeBox state, then it can only fool other nodes if and only if such nodes kept less history, n1 blocks, and the falsified SafeBox had more aggregated work than the honest SafeBox. However, this is not enough to fool the entire network since there exists archival nodes which keep the entire history, and many nodes keep large numbers of blocks. So the theoretical minimum number of blocks an attacker needs to remine is n equals 100, but in practice, it is far higher. If the network keeps a median history of 1,000 blocks, then the security of the SafeBox is equivalent to a blockchain of 1,000 blocks. Formally, the SafeBox model is as secure as the median block history of the entire network with regards to the state attack, but additional security parameters as follows substantially increase the SafeBox's security. The amount of difficulty required to remine a history grows exponentially. This means it's exponentially harder to remine the last 3 blocks than it is the last 2, and so on. Pascalcoin uses a 5-minute block time. Remining 100 blocks with a 5-minute period is far more difficult than, for example, 100 blocks with a 30-second period. Random hash, an innovative ASIC and GPU-resistant algorithm, serves as a powerful deterrent on hash power monopoly. Since nodes require the last 100 blocks minimum, the network median history will never fall below 100. In practice, due to the presence of archival nodes which maintain full history and long-running nodes which maintain large histories, the network median history will always be significantly larger than 100. Current and upcoming synchronization implementations for nodes mean that a state attacker would need to remine far more than 100 blocks. For example, the default setting for nodes who opt for checkpointing instead of continuous history is to download a checkpoint per 2016 blocks or 7 days. As another example, one upcoming implementation involves downloading a checkpoint and then some preceding history. If invalid blocks are found in history, then the compromised checkpoint is eschewed altogether. If a state attack succeeds, then the nodes that had longer histories than the state attack rollback are immune to any balance alteration. If one falls to a state attack, the worst case is that he would simply need to re-download a longer segment of the Pascalcoin blockchain history and recover his balances. The state attacker would be stuck with invalid balances unless he continues to fool others. Technically, no blockchain data in Pascalcoin is ever deleted even in the presence of the SafeBox. Since the SafeBox is cryptographically equivalent to a node with the entire history, Pascalcoin nodes are not expected to contain infinite history. But for any reasons one may have, one could still keep all or some of the Pascalcoin blockchain history as an option. The SafeBox security model actually offers an advantage compared to the full blockchain model in terms of security because it places far less dependence on the full blockchain history, i.e. archival nodes. In the long term, the full blockchain model would inevitably lead to some form of centralization as well as a potential security risk. As a result, the SafeBox security model is at least on par with the full blockchain security model on the macro level. On the micro level, the SafeBox security model is barely diminished to that of the full blockchain model. However, it is still far greater than the simple payment verification (SPV) security model. In terms of cost-benefit analysis, the SafeBox is superior to full blockchain because the SafeBox needs only 1% of storage yet retains 99% of security. Thanks to the SafeBox's design, the user would have full assurance that he is on the longest proof-of-work chain without needing to download the entire blockchain history, a unique innovation that offers many advantages. Commoditization of address space. In almost all other cryptocurrencies, new users can simply create a new address for themselves at will. This creates an infinite address space which can quickly bloat the blockchain, even though the number of users remains constant. If the address space was instead made finite, it becomes a limited resource able to be commoditized. This is how Pascalcoin accounts, PASA, operate. The accounts are limited, but any public key can be associated to it. This creates a natural space-saving mechanism since the chain is not littered with unneeded or used keys. It also disincentivizes spammers, since spammer accounts would be naturally limited and thus easily identifiable blockable. Also, and most importantly, commoditization of the address space facilitates the SafeBox structure itself, which is the key component to achieve infinite scaling. Strong zero confirmation guarantees. Since Pascalcoin is not an UTXO-based currency, but rather a state-based currency, the security guarantee of zero confirmation transactions is much stronger than in UTXO-based currencies. For example, in Bitcoin, if a merchant accepts a zero confirmation transaction for a coffee, the buyer can simply roll the transaction back after receiving the coffee, but before the transaction is confirmed in a block. The way the buyer does this is by respending those UTXOs to himself in a new transaction with a higher fee, thus invalidating them for the merchant. This type of double spend, different from the double spend scenario based on majority hash power, is virtually impossible in Pascalcoin. The buyer's transaction to the merchant is simply a delta operation to debit-credit a quantity from two accounts. The buyer is unable to erase or preempt this transaction from the network spending pool until it either enters a block or is discarded. A double spend attempt would have the same operation identification as the original transaction, which means that it is easy to detect a double spend. Therefore, if the buyer tries to double spend the coffee funds after receiving the coffee, the double spend transaction will not propagate the network since nodes do not propagate a transaction if it double spends a current pending transaction. All Pascalcoin nodes, including those that adopt the lightweight SafeBox model instead of the full history, can easily detect double spends, while doing so in a V4.0 model is relatively inefficient and complex. For even higher security guarantees, the Pascalcoin developers will soon roll out a free and public double spend detection service consisting of a JSON API that links to several nodes geographically distributed throughout the world. For merchants who want high assurances for zero confirmation payments, they can simply query this service after 10 seconds of receiving a Pascal payment. If the service replies no double spend detected, then it is essentially impossible for a double spend to occur, since the majority of nodes are honest and will not propagate a double spend attempt. Such a service would prevent an attacker from launching a double spend from both sides of the globe, which otherwise may have possibly resulted into half of the network carrying the valid transaction and the other half of the network carrying the double spend. The only way an attacker would be able to overcome this additional security measure would be if he colludes with a malicious miner, one that wins the next block after the original transaction, with regards to a private transaction. This is a costly and a probabilistically unlikely proposition. A merchant node will also be able to enable zero confirmation insurance on payments. When a node receives a payment, it then takes out an instant insurance on that payment via a monetized API invocation to a smart contract. If that payment turns out to be invalid, the smart contract automatically compensates the merchant account for the amount of the transaction. The insurance fee is paid by the merchant on the insurance request. No setup, registration, contracts or loss of privacy are required. As a direct consequence of reliable zero confirmation transactions, there is no need for a Lightning Network in Pascalcoin, since zero confirmation transactions are faster and their security guarantees are practically as good, sufficient for micropayments and everyday commerce. Zero-fee transactions. Another unique feature of Pascalcoin is that users are allowed to make one free transaction per block, i.e. every 5 minutes. This gives users 288 free transactions per day, a very reasonable number. The consensus rules for this are simply that a public key can have a maximum of one zero-fee transaction in the memory pool and/or block at any time. This simple approach solves the transaction spam problem, whilst providing users a very reasonable number of free transactions per day. Should one transact more than once in 5 minutes, the very minimum Pasc transaction amount, currently set at 0.0001 Pasc, will be attached as a fee. Should the price of Pasc rises, another zero will be added to the minimum Pasc transaction amount via a Protocol Improvement Proposal (PIP). Zero-fee transactions are achieved on the merits of Pascalcoin's extremely high throughput, in which the fee-bidding competition of transaction priority typical in other V4.0 cryptocurrencies is moot. The fee pressure only starts rising as current throughput approaches maximum throughput, which may not occur even if the Pascalcoin protocol is mass adopted. The fact that there is no fee incentive needed to run a node because of its extremely lightweight overhead beyond the consensus rewards also facilitates zero-fee transactions. Zero-fee transactions apply only to vanilla transactions, namely those that are not private and do not involve smart contracts. Transactions involving privacy and/or smart contracts will involve negligible fees. Account numbers, names, and types. Pascalcoin facilitates value transfer between users by allowing them to transact funds, Pascal or Pasc, to and from accounts, PASA, much in the same way as traditional banking. Unlike most cryptocurrencies, Pascalcoin accounts are simple and easy to remember, e.g. 123456, and not complicated strings which must be copy-pasted or scanned. One of the key features of Pascalcoin is that accounts can have unique names which are publicly visible, much in the same way as the domain name system. This allows a user to receive funds to their email address or chat moniker. It allows a shop to receive payments to their domain name or brand name. Payments still refer to accounts via numbers, but the name is used to look up the account number, just as a domain name is used to look up an IP address. More importantly, account names and types serve a fundamental purpose in Layer 2 applications on monetized API. For example, the account name could serve as a chat room name or a forum name. Account types further serve as a means to distinguish accounts for their use cases. For example, browsing accounts with type =2 could be like browsing a list of chat rooms. How users interact with such Layer 2 applications via monetized API will be described more in this white paper. Smart contracts. Pascalcoin offers powerful approaches to smart contracts due to its SafeBox model. The roadmap includes a Layer 2 overlay network for full Ethereum-style contracts. In particular, smart contracts in Pascalcoin are isolated from the Layer 1 financial network and operate independently on Layer 2. In other words, Layer 1 will be used as a financial settlement network for Layer 2 overlay network. The characteristics of such an architecture are as follows: running a smart contract engine like the Ethereum Virtual Machine (EVM) over Pascalcoin would be possible by maintaining a sidechain pinned to a PASA account. Each PASA has infinite address space for its sub-addresses. Unlike PASAs, infinite sub-addresses do not affect the SafeBox, meaning that sidechain users do not need to own a PASA. Since sidechains are pinned to PASAs, they are intrinsically sharded. Inter-shard communication would simply be transactions between PASAs. Gone are the complications that accompany the traditional sharding approach such as used in Ethereum. Layer 2 sidechains will provide very strong anonymity since funds are all pooled and keys are not used to unlock them. The network would not be impacted by the large volume of transactions since the natural process of checkpointing discards these transactions after 100 blocks. Smart contracts can be developed in any language and target any platform, since smart contract execution and consensus are separate concerns. Layer 2 consensus can adopt multiple forms such as delegated proof of stake, DPoS, and directed acyclic graph, DAG, depending on the sidechain's goals. The infinite scalability of Pascalcoin's Layer 1 will extend to Pascalcoin's Layer 2 as well. This Layer 2 architecture is designed in which the computation is separate from consensus, in effect removing any bottleneck. To be precise, the speed and scalability of Layer 2 smart contracts are fully independent of Pascalcoin's network. Horizontal scaling also exists in this paradigm as there is no interdependence between smart contracts and states are not managed by side chains. One would be able to run the entire global financial system on Pascalcoin's smart contract platform, and it would scale infinitely and securely. Implementing this infinitely scalable smart contract platform as a Layer 2 architecture is the focus of version 5, and a whitepaper add-on for this development will be released shortly. Anonymity due to Pascalcoin's design, transactions to and from accounts can be easily audited by anyone. For many use cases, this is an excellent feature since it makes auditing, reconciliation and accounting very simple. However, Pascalcoin is also committed to providing equally anonymizing features for those use cases where privacy is important. As a result, Pascalcoin has a strong privacy roadmap that has already been partially rolled out. In Pascalcoin version 1, users could transfer Pascals privately using a PASA exchanging approach. Instead of sending Pascals to each other's accounts, the account itself would swap ownership. So as long as the key exchange was transmitted through secure channels, it would not be possible to trace this transaction. Pascalcoin's version 3 added an in-protocol PASA and Pascal tumbling capability. Users who elect for privacy would only need to hit a checkbox, pay a marginal fee, currently set at 0.0001 Pascal, and click send. Under the hood, the wallet will automatically negotiate with other nodes for a set of obfuscating PASA-PASC swaps involving many accounts and merge these all into a single multi-operation. This process can then be chained several times, offering exponentially higher security with every link, rendering the original transaction virtually impossible to decipher. In addition, nodes will be able to earn fees by offering their latent PASC and PASA for these tumbling operations, whilst simultaneously providing a rich set of decentralized PASC-PASA to participate in the tumbling. This would result in a fast, cheap, seamless and genuine anonymity for Pascalcoin users. The Pascalcoin Foundation is also sponsoring R&D proposals for adding ZK snarks, or a similar suitable approach, into the protocol for private balances. It is also investigating smart contract-based privacy approaches. Monetized API due to reliable zero-confirmation transactions, Pascalcoin allows a new form of decentralized application coined here as monetized API 3. In a monetized API, Pascalcoin accounts serve as ports that send monetized messages to other ports. It achieves this by repurposing an account as a named message queue and by utilizing operation payloads. In Pascalcoin, operations can carry any arbitrary 256-byte payload of user data. Payloads can be public or encrypted. This unique capability allows operations to embed Layer 2 protocols in much the same way that HTTP lives inside TCP. The difference here is that the protocol messages carry a financial weight and as a result can be used to conduct granular economic communication suitable for algorithmic autonomous micro-commerce scenarios. Some examples of applications have monetized API are as follows. Examples: Pascal Chat. An account can serve as a chat room where the account name is the room name. Operations payloads to the account can contain the user's chat message. The user's handle would simply be the sender's account name. These chat rooms can be used for trading goods and services in a decentralized manner. Anonymity can be enhanced via other Layer 2 applications. Users can settle payments for goods by attaching funds to private messages between themselves. Monetized content, a Pascalcoin browser plugin that pays content providers for content on the fly. The payment itself contains info to allow the server to unlock the content for the browser. This could be used for monetizing news, blogs, ebooks and social media content. One-click e-commerce, a one-transaction e-commerce site whose shopping cart is reduced to a single payload code. The buyer merely sends a Pascal payment containing the payload code, and when received by the merchant the order is executed for the buyer. No credit card numbers or complex payment gateway integrations are required. Anonymity mixers, accounts can receive funds from other accounts and then resend those funds using complex financial routing information encrypted within the sender's payloads. The mixer can split delay-relay loop payments arbitrarily, thus sufficiently obfuscating the sender, receiver and quantity from taint analysis. Layer 2 sidechains. Since messages to from an arbitrary account X can be used as a message queue, it is possible to construct Layer 2 protocols for managing a sidechain by monitoring messages to X. The sidechain's validity state is governed by the Layer 2 protocol embedded within these Layer 1 payloads. The owner of X serves as an authority on a mono-federated sidechain suitable for dApps. Owner-free or non-federated sidechains can be constructed by associating a proof of burn key on an account. Federated sidechains will be possible when Schnorr multisig is implemented, whereby members of the federation will be comprised of the account signatories. An example of an actual monetized API, and the first one ever created, is getpasa.com. It works by listening on account 7744 for incoming transactions of 10 pascals or more. When a transaction is sent to 7744 containing 10 pascals or more, its payload is examined for the presence of a public key. If nothing is found, the transaction is discarded. If a public key is found, the service then finds a free account in its inventory and sends it to the key it found. This allows new users to purchase an account in a one-step process that sends a single message containing the order and payment combined. Data transfer. Pascalcoin's SafeBox architecture allows accounts to transfer data between themselves in a secure and private manner. This is possible due to the ability to attach a 256-byte payload to each transaction. Via this mechanism, a user can split any file into multiple segments and transfer each segment as an operation to the receiver. This data can be ECS encrypted so that only the receiving account can reconstruct the original file audio-video. It can also be ACE encrypted so that bearers of the shared secret can reconstruct the file. Alternatively, the data transfer could be public and available for everyone. Since Pascalcoin's nodes need to keep only 100 blocks, blockchain-based data exchanges do not result in a blockchain bloat. This Layer 1 feature can be leveraged by Layer 2 smart contracts to provide infinitely scalable global data storage networks, DSN, and even decentralized document management solutions for both private and public data. Self-funded and self-governed community. Pascalcoin was a 100% fair launch without any pre-mine, ICO or investment rounds. The Pascalcoin developer community are independently wealthy, self-funded evangelists who develop and promote this game-changing technology. The development team, led by Albert Molina, are mature, exceptional developers with proven track records of delivering high-quality software. The developer fund exists as a percentage of mining rewards as voted by the Pascalcoin community. This developer fund is set as 20% of the mining rewards and is governed by a decentralized autonomous organization, DAO, facilitated by the Pascalcoin Foundation. This DAO will eventually be transformed into an autonomous smart contract platform. Not only are the developer fund disbursements voted upon the community, but Pascalcoin's development roadmap is also voted upon the community via the Protocol Improvement Proposals, PIPs. This decentralized governance also serves an important benefit as a powerful deterrent to fork wars that befall many cryptocurrencies. Written in free Pascal, Pascalcoin was designed and written from scratch in the free Pascal programming language without copying a single line of code from any other project. The Pascal programming language has evolved far beyond the days of Turbo Pascal. Free Pascal is a modern object-oriented language with advanced features such as generics. It was originally designed as an alternative to C, and with its modern advances and upgrades, has become a great language for writing high-performance, cross-platform native code. While the free Pascal programming language is used for Pascalcoin's core development, dApps and any external implementations based on Pascalcoin can be written in any language. One advantage using the free Pascal programming language is that it raises the barrier higher for forking a clone cryptocurrency based on Pascalcoin. It would be almost impossible to fork Pascalcoin unnoticed due to its Pascal-based codebase, unless one masters the Pascal programming language then rewrite the entire codebase into a different language. Pascalcoin architecture. The SafeBox is opposed to a series of blocks containing transactions records going from one address to another. Pascalcoin uses two components, the SafeBox, containing all current account balances, and blocks linked together to form a blockchain. Just as with Bitcoin, mining nodes are responsible for creating a new block. All nodes update their copy of the SafeBox independently of each other when new blocks are announced. As part of this task, nodes need to update the balances and other fields of existing accounts based on operations in the block as well as create a new account segment containing brand new Pascalcoin accounts awarded to the winning miner. First SafeBox. Before the first block is created, the very first SafeBox number 0, Genesis SafeBox, is created which does not have any account in it. Miners will seek a new block for the blockchain via the proof of work, where the hash of Genesis SafeBox is used as input. Once this first block is created, a corresponding new version of the SafeBox is created along with an account segment containing n new accounts, where n is defined by the protocol and is set to 5 in Pascalcoin version 2. Now the miners will start working on the next block of the blockchain in order to generate the next version of the SafeBox which will include new pending operations circulated by nodes. Operations similar to Bitcoin and other cryptocurrencies, blocks in Pascalcoin are containers for transactions called operations. They are referred to as operations as they are generalized transactions and perform more than simply transfer funds between accounts. For example, there are operations to change an account's key, to change its name, or to mark it for sale, etc. The most important and common operation is the transaction operation which transfers funds between accounts. Checkpoint torrenting. In upcoming releases, a vastly improved checkpoint distribution infrastructure will be soft forked and called checkpoint torrenting. The full process will work as follows. The checkpoint is persisted as multiple same-size chunks of raw data. When a new node comes up, it will query from multiple nodes for the latest checkpoint information consisting of the checkpoint block number, SafeBox hash of the checkpoint, total work of the checkpoint, Merkle tree of the checkpoint chunks. The new node can then determine the correct checkpoint to download by simply selecting the one advertised with the most total work. The node then downloads the checkpoint chunks simultaneously from many nodes. During transmission, chunks are significantly compressed which greatly improves synchronization speed and reduces network traffic. Chunks are then independently validated using the provided Merkle tree, see diagram below. Once all chunks are downloaded, the checkpoint is reconstructed and verified for structural integrity. The total work is then recalculated and compared to the advertised total work from the beginning of the synchronization process. If the checkpoint turns out to be invalid for any reason, it is discarded and the advertising nodes blacklisted. The synchronization process then repeats ad infinitum until a valid checkpoint is downloaded. If the checkpoint is valid, it is adopted as the SafeBox and the usual block synchronization process resumes. At most, a new node will only ever need to download 100 blocks in order to be fully synchronized. The next page contains the diagram of the checkpoint Merkle tree. POSA distribution models. Commoditization by design. POSAs need to be commoditized by the SafeBox's design, meaning that POSAs cannot be obtained at no charge to prevent systematic abuse. This raises two issues that are tackled appropriately in POSA distribution models as a chicken and egg problem. How would one purchase a PASA using Pascal in the first place if one cannot obtain Pascal without a PASA? How would the price of PASAs stay low and affordable in the face of significant demand? With regards to the chicken and egg problem, there are many methods, some finished and some unfinished, to obtain a first PASA, which may be free depending on the method used. It is worth noting that, while PASAs need to be commoditized to a degree as part of the SafeBox's architecture, they will always remain affordable at a very inexpensive price, as well as continually become easier to acquire over time as more acquisition methods are implemented. First PASA acquisition methods. Free first PASA acquisition methods. Submit a SMS message through freepasa.org, and a free PASA from Pascalcoin Foundation will automatically be granted to a public key. Obtain a free PASA from Pascalcoin Foundation by simply activating your Android iOS wallet using a SMS number. Send a Pascalcoin related tweet reaching at least 10 people, and a free PASA will automatically be given from the Pascalcoin Foundation. Obtain unlimited pseudo PASAs in version 5 with a layer 2 implementation. Minimal charge for first PASA acquisition methods. Purchase a PASA at an inexpensive price from getpasa.com or pasquallet.com. Obtain PASAs via mining rewards, currently set as 5 PASAs per 50 Pasc. Purchase a PASA OTC from someone. PASA economics. As for ensuring the PASA market at large remains inexpensive and affordable, this would be achieved in 2 ways: decentralized governance of the PASA economics unlimited, and free pseudo PASAs based on layer 2 in the next version release, which would reduce demand for layer 1 PASAs. The decentralized governance of PASA economics would work as follows. If the price of a PASA increases, then there are many available options via decentralized, community-driven PIPs to keep the PASA price low, including but not limited to increasing the supply of PASAs mined per Pasc, currently set at 5 PASA per 50 Pasc, issuing accounts per block in accordance with Moore's law, dynamic and instant account creation using new and yet to be implemented create account and destroy account operations, one-time issuance of millions of new accounts to entities, Pascalcoin Foundation, pasquallet.com, etc. For secure, decentralized distribution methodologies. Account recovery. Coin rot is an economic issue afflicting almost all other cryptocurrencies. Coin rot is the phenomenon of coins being permanently lost due to lost corrupted keys and/or natural death. It is estimated that 20% of bitcoins have already rotted. Coin rot as applied to Pascalcoin, especially in the context of PASA, poses a minor but unnecessary weight on the SafeBox's architecture. As a result, account recovery will be executed after 4 years of full inactivity, i.e. no single transaction from the PASA of interest, and the contents, both Pasc and PASA, would be distributed to miners. However, this 4-year period will likely be extended to a 10-year period with an upcoming PIP. Random hash algorithm specification. A low memory, GPU and ASIC-resistant hash algorithm called random hash is proposed to resolve and prevent dual meaning and mining centralization. Random hash, defined first here, is a high-level cryptographic hash algorithm that combines other well-known hash primitives in a highly serial manner. The distinguishing feature is that calculations for a nonce are dependent on partial calculations of other nonces selected at random. This allows a serial hasher, CPU, to reuse these partial calculations in subsequent mining, saving 50% or more of the workload. Parallel hashers, GPU, cannot benefit from this optimization since the optimal nonce set cannot be pre-calculated as it is determined on the fly. As a result, parallel hashers, GPU, are required to perform the full workload for every nonce. Also, the algorithm results in 10x memory bloat for a parallel implementation. In addition to its serial nature, it is branch-heavy and recursive, making it optimal for CPU-only mining. Within the scope of changing the hash algorithm, other hash algorithms were considered like equihash. However, these were ruled out due to their excessive memory consumption, contradicting Pascalcoin's vision of globally decentralized network that runs fine on low-end hardware available anywhere on this world. Requiring voluminous amounts of fast memory to validate blocks is not consistent with this vision. Overview 1. Hashing a nonce requires n iterations, called rounds. 2. Each round selects a random hash function from a set of 18 well-known hash algorithms. 3. The input at round x is salted with the outputs of all prior rounds. 4. The input at round x is salted with the output of all prior rounds of a different nonce randomly determined. 5. The input at round x is a compression of the transitive closure of prior neighboring round outputs to the size of 100 bytes. 6. The output of every round is expanded for memory hardness 7. Randomness is generated using Mersenne-Twister algorithm 8. Randomness is seeded via MUR3 checksum of current round 9. The final round is then hashed again via SHA-256, in keeping with traditional cryptocurrency approaches. Random hash analysis CPU bias. The random hash algorithm is inherently biased towards CPU mining due to its highly serial nature. In addition, random hash allows CPU miners to cache the partial calculations of the other nonces and resume them later. This allows CPU miners to save 50% of the work during mining. This is formally proven in a separate random hash white paper, but is easy to grasp as follows. In order to complete a nonce to round n, another nonce needed to be completed to round n1. The other nonce requires one more round to complete, saving 50% of the work. This optimal nonce set cannot be pre-calculated and can only be enumerated. As a result, serial mining, CPU, does 50% the work of parallel mining, GPU. Memory complexity. Random hash is memory light in order to support low-end hardware. A CPU will only need 5 MB of memory to verify a hash. During mining, it will need 10 MB per thread when utilizing the 50% bias mentioned above, an easy requirement. It's important to note that random hash consumes most of the memory in the initial rounds and little in the final rounds. This is deliberate in order to hinder GPU mining. For example, suppose a GPU has 5 GB of memory. A naive hasher could attempt to batch 1000 nonces for parallel evaluation, since each nonce requires 5 MB. However, since each nonce depends on 15 other nonces, and most of the 5 MB per nonce is consumed in the early rounds of those nonce evaluations, the GPU will run out of memory quickly. The batch size needs to be divided by 15 in order to utilize the 5 GB effectively, which means most of the GPU memory is wasted on partial nonce calculations from the early rounds. In that scenario, the GPU can only effectively compute 20 nonces per 1 GB of memory. A CPU can easily compete with this and implement intelligent parallel mining by using other threads to mine the less partially calculated nonces. This could potentially give a CPU significantly greater than 50% advantage, but this approach needs further research. GPU resistance. GPU performance is generally driven by parallel execution of identical non-branching code blocks across private regions of memory. Due to the interdependence between hashing rounds, the slower global memory will need to be used. Also, due to the highly serial nature of random hash's algorithm, GPU implementations will be inherently inefficient. In addition, the use of Mersenne-Twister to generate random numbers and the use of recursion will result in executive decision-making, further degrading GPU performance. Most importantly, since nonces are interdependent on other random nonces, attempts to buffer many nonces for batch hashing will result in high memory wastage and 200% more work than a CPU. This occurs because each buffered nonce will require calculation of many other unbuffered dependent nonces, rapidly consuming the available memory. A CPU implementation does not suffer this since the optimal nonce set to mine is enumerated on the fly as each nonce completes. Another important feature is the pattern of memory expansion factors chosen for each round. These were deliberately chosen to hinder GPUs by amplifying the memory needed for their wasted calculations. As a result, it's expected that GPU performance will at best never exceed CPU performance, or at worst perform only linearly better, not exponentially as is the case now with SHA-256D. A SIC resistance of SIC resistance is fundamentally achieved on an economic basis. Due to the use of 18 sub-hash algorithms, it is expected that the R&D costs of a random hash ASIC will mirror that of building 18 independent ASICs. This moves the economic viability goalposts away by an order of magnitude. For as long as the costs of general ASIC development remain in relative parity to the costs of consumer-grade CPUs as of today, a random hash ASIC will always remain not worth it for a rational economic actor. Furthermore, random hash offers a white ASIC breaking attack surface. This is due to its branch-heavy serial, recursive nature and heavy dependence on sub-algorithms. By making minor tweaks to the high-level algorithm or changing a sub-algorithm, an ASIC design can be mostly invalidated and sent back to the drawing board. This is true since ASIC designs tend to mirror the assembly structure of an algorithm rather than the high-level algorithm itself. Thus, by making relatively minor tweaks at the high level that necessarily result in significant low-level assembly restructuring, an ASIC design is made obsolete. So long as this tweak to break ASIC policy is maintained by the Pascalcoin developers and community, in addition to the economic impracticality of building a random hash ASIC resistance is guaranteed. Random hash variations of random hash can be made by varying n, the number of rounds required, and m, the memory expansion. For non-blockchain applications, the dependence on other nonces can be removed, providing a cryptographically secure general-purpose, albeit slow, secure hasher. It is also possible to change the dependence graph between nonces for stronger CPU bias. For example, requiring the lower rounds to depend on more than one nonce and the upper rounds on no nonces at all may allow further CPU versus GPU optimization, and similarly for memory expansion factors. Extra, albeit unnecessary, strengthening can be added in the initial rounds of hashing by using the hash of the block header for seeding instead of the block header itself. In the analysis of the author, this is unnecessary and has subsequently been removed. Random hash whitepaper. There is a separate random hash whitepaper written that goes into greater details on the algorithm. This whitepaper provides pseudocodes and reference implementation codes for the algorithm as well as formal proofs